Okay, hello everybody. Hello, may I have your attention? Welcome to our next Backend meetup. I'm so excited to see so many of you. This meetup called Summer with Backend is hosting by Mews, Ataccama and Wrike. My name is Carolina and I work as a tech community coordinator in Mews. Couple of information about the program. So after the amazing talks delivered by our amazing speakers, who will be Marek Třešňák from Mews, Václav Brodec from Ataccama, and Daniel Grankin from Wrike, you can move to the terrace to the 11th floor, where you can have a free food and free drinks. To this, you will be granted with the tapes as we give you on the registration. And without further ado, I will give floor to Marek. Thank you.
All right. Thank you, Carolina. So I'm Marek from Mews. You can read my name here because I didn't put it in a presentation. And how do I actually switch to the presentation? No worries. Cool. So everybody can see that. All right, so the first talk is going to be about storing datetime information and answering the question of, is UTC really the right way to do it, right? If you don't know why I'm even asking that question, don't worry. Hopefully you will get it from the talk. Cool, so let's start with what is Mews. Mews is basically a company that develops solutions for the hospitality industry, right? We develop systems that are internally used by hotel receptionists, hotel cleaners, but also guests of those hotels. So the thing that you can see here is basically a dashboard, the main screen that we have in the system, just so we have an idea of what the system looks like. Cool. So jumping to the next screenshot from the system, here is a screen that hotel receptionists will see very often. And that screen is something we call the timeline, right? The timeline is an overview of the reservations that you have in your hotel. You can see which reservations are assigned to which rooms, when they start, when they end, who the guest is, all of that information. You will probably notice, or you will guess from the description, that as a hotel system, there's a lot of daytime information that we need to store. Just on this screen, you can see that for each reservation, we need to store the arrival and departure time, for example. And that is going to be the example that we will be working with throughout this presentation. Cool. The next screen is something completely different. This is a map of the world, as you probably know, showing hopefully all the time zones that we have in the world. You can see there's a lot of them. And the reason I'm showing this is that we are a system that operates globally. And that means that we need to combine the two requirements, right? Being able to store all of those datetime values that we need to have in the system, and being able to work with them in all the time zones of the world. Now, back to our example. So when you're designing a system like this, you might start with some screen that is going to allow you to create a new reservation in the system, right? Without reservations, it doesn't work very well. And you might be thinking, right, I have these arrival and departure times that I get from the user, but how do I store them in the database? Well, the simplest way to do it is just take the values that you get from the user and just store those in the database. I would say that's kind of a naive approach, but oftentimes there's nothing bad with being naive. So you might do that. That's definitely an option. But if you start searching the internet for some alternative ways, if you think like maybe in the naive way is not the best way, you might find an answer like this. Someone on the internet with high reputation on Stack Overflow might tell you that you should always store your times in UTC and you should convert them to local time every time you're displaying them. Well, what does that even mean? UTC is something that you can imagine as a master time of the world. Some universal clock that shows some true time that you can then convert to each time zone. That basically gives us some standard time that we can all refer to, right? Even though for most of us, the local time in our own time zone is obviously the most important one. How do we do such a conversion from UTC to our local time zone and back? There's always something that's called a UTC offset, right? For every time zone, we have a UTC offset, and that UTC offset pretty much tells us what's the difference between our time zone and the UTC. And in order to know which offset we should use to perform a conversion from UTC to local time or from local time to UTC, we are using something called the TZDB, time zone database, right? In the time zone database, we have basically a simple table where we can just look up the differences for our time zone and then do a simple subtraction or addition operation to get the local time or the UTC. That's pretty simple. So jumping back to our answer that we found. So what those people on the internet are telling us is that when we get the value from the user, right, and that's basically these two values that we get, we should just look up our offset that you can see on the right side. So let's say we are running a hotel in Mexico, and that offset is -5 hours, and we should kind of apply that and calculate the UTC time that we will be storing, right? So in this case, we're translating 6 p.m. to 11 p.m. because the difference is 5 hours, and we know that our hotel is basically 5 hours behind UTC. So that's an interesting advice. Store that. What those people also tell you is that if you follow this, you will never have to deal with time zone issues again in your application. So even if you don't know what those time zone issues are, following that advice might look very reasonable. And yeah, the second part of the answer that we found on Stack Overflow was just showing how to interpret those values again. There's nothing surprising here. You will just take the values that you store in your database, you will take the UTC values, you will apply your conversion, and you will end up at the same time that was entered by the user. So at the time that you're designing a screen that is showing a detail of a reservation, you're going to be showing basically what the user put in. Simple. So that's what we did, and we were quite happy with that for a couple of years, right? Until a few years later in Mexico, something happened. That something is a call from our users telling us that if they put in a reservation in the system, it shows up with a completely different times, right? You can see that basically here. So that's what they were complaining about. After some investigation, what we learned is that it's not a completely different time, it's just a time that is different by an hour. So that started being suspicious. So we started investigating further, and this is what we found. The first thing that we realized was that we were doing the two conversions from local to UTC and from UTC to local on different sides of the application, right? The first one we were doing on the server, the second one we were doing on the client. So we investigated some more, and what we found out was that we were using a different offset on the server than we were using on the client. At this point, the solution might look easy, that you would just use the same offset everywhere, right? Use the same time zone database because there's obviously some difference. But if we were to do that, and we would just take the server's time zone database and apply it to the client as well, we would be working with an offset of -5 hours, so everything would seem all right, but maybe it wouldn't be. Let me explain that. As part of the investigation, what we learned is that we were using a time zone database version that you can see at the top, but the current version used by the client was the one at the bottom of the screen. And there were multiple versions in between. So that didn't seem like a good solution to us because we would still be stuck with some old version of time zone database. So what we decided to do is also kind of obvious, and that was upgrade the time zone database to the newest version. What could go wrong with that, we thought. Until we tried it. Then we learned what could go wrong. In here, you can see basically a comparison of the view of our database seen with the different versions of TZDB. On the left side, you can see the old one, with the offset being -5 hours. On the right side, you can see the new one, where the offset is -6 hours. And on both of them, you can see our data stored in the database, stored using that -5 hour offset. So when we upgraded the time zone database in our application, what would happen is that the data that we stored in the database would be interpreted using the new offset, as you can see on the right side. But that also means that with the new offset, we would shift all the values that we had in the database by an hour, which is not good, which would affect all of the future reservations that we have in our hotels. Right? All of them would start exactly an hour later than they were originally put in the system. And that's not good. That's just like losing information. And apparently, it's not acceptable for a hotel to make a guest wait another hour because of a flaw in the system they're using. All right. So after some solutioning around this, what we were thinking we would do is that before the upgrade of the database or as some part of the process, we would just recalculate the values that we have in the database to those that would be interpreted correctly using the new offset. That's a solution that although it would work, has a couple of problems. And the first one is that we're now only talking about the reservations table and only about a subset of it, but there are 178 other tables in our database that we would have to go through, look at the data that we have there, and decide if that data is something that we need to convert, and do all the work with the conversion. So that's a pretty big step and a pretty big chunk of work. Another problem that we would soon discover is that even if we did that, during the conversion of those values, we would have no way of knowing which time zone database version was used to store the value, right? And that is a problem because if the conversion fails somewhere in the middle, you can't reliably tell which values have been converted already and which have not. So therefore, that would mean that we could potentially lose client data as well because we couldn't just tell which half we should still convert and which we shouldn't, and we would mess it up again. And then obviously, all of those problems are solvable, but what we would have to do is that we would have to solve them every time we updated the time zone database, which, if you remember from a few slides back, is released a couple of times a year. So we would have to go through that process a couple of times a year. So after learning this, we thought, isn't there a better way to solve this? Isn't there a way to solve this without having to do all of those recalculations and maintaining all the code that recalculates it multiple times a year? And what we decided to do was take a few steps back, right? And think maybe we should go with the simplest solution possible. What could go wrong with that, right? There's probably something those people on the internet think about the solution that disqualifies it in their eyes, but maybe it's not that bad. So let's take a look at it. Let's see if it works. What we learned, here's the solution again, right? Here is the solution that we were now investigating. Just taking the values that we get from the user and storing those values in the database. Problems with this approach would be completely different than with the approach that we were using until that point. You can see that when we store the values as they are input by the user, it doesn't matter which UTC offset is currently applied in a time zone, right? The values just don't change, and the way we interpret them doesn't change either. So that's good. That means our biggest problem just disappeared. So what are potentially some new problems that appeared with this solution? Well, one problem that is often mentioned is the problem with ambiguous time. Just to explain this one a little, you might already be guessing what problem that is. But in most of the time zones, we have the daylight saving time, sometimes called the summertime or other names. And all of you living in a time zone that has that, which Prague is, know that once a year the clock goes back an hour, right? In our case, it's going from 3 a.m. Back to 2 a.m. and basically an hour with the same calendar, like in the same calendar day, 1 hour appears twice. So in this case, the time 2:30 happens twice during a single day. If I tell you, meet me at 2:30 on that date when the time changes, you might be waiting for an hour, right? Because maybe I meant the other 2:30. So the problem with ambiguous time is that if you store local time only, you have no way of knowing which one the user that put it in meant. This might, but also might not be a problem for your use case. But it's a good one to keep in mind, and it's a problem that you don't have when you're working with UTC only, because there's no daylight saving time changes there. Another problem with this approach is that if you want to query your database data across different time zones, then it's kind of complicated if you only have local times, because you just can't compare a local time in a time zone of Hotel 1 to a local time stored in a time zone of a different hotel, and that has the time zone also different, right? A solution to this is basically illustrated here, and that is kind of storing the UTC time as well, and just using that UTC time for your database queries, potentially even for identifying the precise moment in time that you meant. Obviously, this brings us back to the solution that requires a recalculation every time that you update your time zone database. But in our case, what we learned is that the values where we would also require to store the UTC value, there's much fewer cases than we have now. So it's kind of a solution that requires some overhead, some recalculation every time you update the time zone database, but you might not need to do it in a large scope, so it might be acceptable. There's probably no reasonable way around that. Cool. So after going through this little story, we asked the question of, is there then a right way to store datetimes? Is there anything, is there any approach that we could universally apply everywhere without even thinking about it too much? And unfortunately, our answer to that question was no. The way we store datetimes always needs to depend on the meaning of the values that we are storing. If we are storing local values that local users in some local time zone are going to be looking at, then it definitely makes sense to store them as local time. But in cases where we need to uniquely identify a point in time, then it still makes sense to use UTC, right? Because we might never need to convert the time to local time, and if we do, maybe it's fine that upon an update of the time zone database, this will change. So just to give an example of a use case where we are keeping the UTC datetimes, that could be scheduling of background jobs, for example, right? That's something that is only used internally by the system, doesn't need to be interpreted in a local time zone. Therefore, we don't have any overhead storing the data, the UTC datetimes there. Cool. I put this slide in at the last moment, but if this sounds interesting and you are looking for a job, then you can scan this QR code, and that leads to Mews careers page. So I will leave it here for a minute, or maybe 10 seconds.
Vašek, the floor is yours.
Hello. All right, so I'm Vašek from Ataccama, and I promised the topic of low-latency data processing scheduling under constraints. It's a bit of a mouthful, right? And I hope I will deliver on explaining every single part of it. Yeah. So let's start with a bit of a warning. Yeah? This is not going to be an inspirational story, right? Like, this is just a, let's say, report of something that we made and we are not entirely sure about, and we just have to live with it. Yeah. Please don't take any inspiration from that. Yeah. Okay, now to some context. So Ataccama has this nice vision that we offer to our customers, which is we are going to provide you with one unified platform for all your data management needs. And it starts with master data management, where we offer, I don't know, like providing some sort of gold record for your business entity. We offer data governance, where you can basically access and manage access to certain data within your company, this sort of stuff. But traditionally, we are very strong with data quality. And the reason why is that we offer our users a combination of two killer features. One of them is the ability to define business rules, even for a non-technical user, right? Like, even if you can't code, if you know just the basic stuff, you can just go to the application and start to define rules like the one which would detect social security number. And you can do that with a combination of actually being able to run this rule on top of plethora of data sources, right? Starting from the very archaic ones to those fairly recent ones, right? So from Snowflake and up to the, I don't know, like SAP connector, something like that, yeah? Okay, the actual story starts some time ago when one of our biggest customers, well, they got into the trouble. Large customer, quite a lot of own customers on their own, petabytes of data, thousands of individual data sources, and well, they suffered a data leak. And I'm not entirely sure what happens then, but one of the outcomes was that they are supposed to audit any sources for presence of any personal PII data, basically the data that somehow disclose your personal information, right? And funnily enough, we won that deal. And we won it through the combination of the fact that we do offer those killer features. We allow them to define those rules, we allow them to run those rules on top of various data sources. And even now, data classification, or rather the scanning for PI data, is not our specialization. We want a deal, and now it's our task to actually deliver on the promises that we made to them, that we are going to able scan all the petabytes of data across the multiple data sources with some daily throughput, which is pretty ambitious, or was pretty ambitious at the time when we rolled out our new version of the platform, right? Okay, I will focus now just on the data processing itself, because it was an experience even for the other parts of the platform, but I'm here mainly for the data processing. And the reason why we made it work was because of the simple fact we had this nice architecture. It's nothing groundbreaking. There is some gateway control module which receives the job submissions, which basically say, hey, I want to scan for PI data on this data source. And this gateway control module distributes those jobs across various agents, which are usually located close to the data sources, so that you don't transfer data outside of the realm where the data source lies. Yeah? And the idea is that, well, if you have a lot of data, you will just add few more agents, couple more agents actually, right? And everything should ideally horizontally scale because of that. Well, situation wasn't that simple. There are some constraints, as I promised in the title, right? So one of the constraints is the actual location of the data source and the engine which is supposed to connect to it and access the data. Because like you can access all data sources within the company from a single engine. That's virtually impossible. It's located within certain within certain network, this sort of stuff. Also, the engines are not infinitely vertically scalable. They do have certain performance limits, and that's another constraint. The more nasty constraint than this is the fact that even the data sources are limited in their performance. You can't open unlimited amount of connections to a certain data source. And that was something that became painfully obvious once we start to scale the engines. Once we started to do that, now then we noticed that, hey, we are actually observing a lot of the jobs failing because of that, because the data sources couldn't handle the load. And last but not least, another nasty constraint here is that we actually guaranteed certain ordering or guaranteed total ordering on top of the job submitted to our processing platform, which in retrospect showed, well, it has shown to be a big problem for us, as you see. And there are also some other requirements. I put it here because a large portion of the solution had to deal with the fact that we kind of promised that the solution is going to be highly available. Yeah? All right. So as I said, we kind of expected that if we add more engines, that we'll observe something like this, right? That once you add, let's say 20, once you add an engine which can do 20 jobs in parallel, you will see like these steps, which will show that the performance overall grows. Maybe with some minor fluctuation as the jobs arrive and they are distributed across the engines. Unfortunately, this one wasn't the case. And this wasn't the case for a simple reason that we are not doing things in the right way. Especially if I refer to the right side of this slide, when we were trying to protect data sources from being overloaded, we implemented some additional logic on top of the queue of the jobs that were coming to our processing engines, which just took too much time, so we did not properly utilize all the data sources or all the engines, which showed here as this ugly fuzzy graph, which tells you that, hey, actually the engines are starving for new job submissions. They're just idling, which made our customer not very happy because they were paying for all the expensive resources, right? Okay, so what did we do wrong? We did a pretty bad thing. We misused the database. We basically implemented all this additional framework on top of the simple queue in the memory, we basically read candidate jobs from the queue, and then only decided, okay, this job is actually supposed to arrive at this particular engine, and this on another one. And also make sure that you do not overload this particular data source. And we did it in 2 steps, unfortunately. So first, read the page from the database, and then further filter it out, which, well, was the actual cause of the performance issues that I showed you on the previous graph. Yeah, but basically, if you got really unlucky, what could easily happen would be that we would scan through the whole queue in the database and only pick up some interesting job for the processing platform to process only at the very end. All right, so how to get out of this mess? Simple solution as they are. We don't need to compute the distribution of the jobs at the time that we pick up the jobs from the database. We can actually pre-compute it, right? So we took the constraints and we start to pre-compute them. So at the moment that there is actual need for the distribution of the job, you already know where the job is supposed to end up. Simple as that. One kind of controversial thing that we did was that we actually ditched any processing in the database itself. We said, okay, even if we use just the memory, we can actually make the representation of the mapping between the jobs and eventually the engines and the data sources efficient enough so it can easily fit even with large number of jobs in the memory of the control module. And that proved to work quite nicely. Yeah. Now, until this time, I think we are kind of sure about the solution. The problem started to appear once we were asked to extend it to operate it in multiple replicas. And the reason for that wasn't the actual original customer. The reason was that we are still developing a product, not a project. So we actually had to take the same solution and applied it on another customer, right? Which had the requirement for the solution to being highly available. And unfortunately, we chose a solution which was highly available in the active mode. So we actually promised that we are going to run multiple replicas at the same time, which are ideally going to spread the work among them. Well, this has soon become a problem, especially considering 2 constraints that I already mentioned. The prioritization of the jobs and the fact that we in no way said that you are supposed to take one engine and apply it to just certain set of data sources. We basically allowed for overlaps between the engines and the data sources, which further complicated the solution. Okay, let's come back to the solution for multiple replicas, right? We already know that we compute the solution in the memory of each replica, and now it's time to kind of figure out what can go wrong if you do that, right? And basically decide where the replicas can diverge under what circumstances. And yeah, it can happen whenever a new job is enqueued. It can happen whenever the job is reprioritized, that word, right? And also whenever the job changes its state, right? For example, when it's finally decided that it's going to be submitted to certain engine. And the simple fact is that, yeah, the replicas actually need to sync on that state so that they actually make good decisions. And we originally thought this is going to be a problem, but it turned out to be not to be that problem. Oh, okay. Great. After some optimization, we are able to quickly read the states from the database and update replicas. So problem solved. Where it became more complicated was if we wanted to ensure that, for example, the job priorities are followed. And what we realized is that, yeah, we actually cannot ideally scale because this totally leads to a centralized solution, which is not something that you would like to solve once you really want to scale, right? Because then you do have a choke point. You do have one single central point where all decision has to happen, at least for the allocation part. Yeah. All right, how did we actually solve that? So we said, okay, we need to decide where the jobs end up within a single transaction. It has to be done at one of the replicas. Also, we chose to follow an optimistic approach. Instead of choosing one leader and let him decide, we chose to let all the replicas do the work, and only if some conflicts do happen, roll back and try again. And that proved to be the winning solution. Still, we had to solve some problems, right? Because, as I said, conflicts can still happen. If two replicas decide to work on the same job at the same time, one of the replicas has to basically start again. And then you have to solve problems like deadlocks, right? Basically, deadlocks as you are used to from any concurrent computations. Again, easily solvable by the fact that we were able to establish order on the jobs, replicas, and the engines, and always log them in the strict order, always in the same strict order as established. And this is the final solution. I bet you can't really see it, right? So one thing that is to note here, it did scale, but just on the submission threads here, right? This is something that you can really scale and that we were mainly interested in because these threads ideally should be always occupied by doing some useful work. The part which does not scale, which needs to be centralized, is the decision-making process that we had to establish on the multiple replicas. And yeah, in that case, you really do have to lock the queue at least for a certain time until you decide about the distribution of the jobs. It does have one significant benefit as opposed to the solution if we choose just one leader to do all the work. As I already mentioned, that we not do just the job processing, but we also allow interactive work with the data sources. Maybe I did forget to mention it, but we do that. And in that case, you can actually skip some of the phases until the allocated resource is one, because in that case, you still want to allocate the data source because you do use up a connection if you try to do some interactive work. But you are not really concerned about the planning among the engines because the interactive work is usually pretty undemanding. All right, I glossed over a few details. There is one thing that I cannot really miss out on, and that was the fact how we tested it. I mentioned that we worked and relied on the transactions working correctly. We did rely on rollbacks. We did operate in multiple replicas. And for that case, we actually built a simple framework which tried to intentionally destroy the solution. So we started the transaction on one of the replicas. There was an agent which was observing whether we are actually in a transaction on one of them. And if that was the case, it tried to kill that replica. And we did observe whether the other replicas were able to step up and finish the work. All right, that's it. Maybe a few lessons learned. Always try to constrain the requirements. The simple fact that we allowed for unlimited prioritization of the jobs, that we allow for an overlap between the engines and the data sources, it complicated the solution several times. If we would restrict the users so that they can actually access certain data sources just from certain engines, we would eliminate all sorts of problems. And yeah, that's the main takeaway from today. So I'm happy to answer any questions that you might have. And also, yeah, there are some credits because I'm really here just substituting for our proper engineers. Yeah.
I would like to invite you to stage Daniel from Wrike.
Thank you. Hi, everyone. I am Daniel. I'm a Wriker. I'm an internal backend unit engineer, and we're improving the technology stack. The recent transition to Java 17, it wasn't too easy, but like still, we watch out for performance, monitor the production, and we're also in charge of a user data encryption. So today I'm going to share one of the stories we have in Wrike, one of the feature story and how we overcome what was initially thought as minor cobblestone, but we needed to keep more attention to it in order to do it. Let's talk first about the environment of the problem. So Wrike is a software as a service. That means that we store all of the user data in our data centers and provide to the user on demand. And while our data servers and our infrastructure is generally very robust and we follow the procedures, everything is eventually bypassable in terms of security. So Wrike designed a feature called the write lock. It's a secure data storage management system layer, which utilizes cryptography. And in order to understand it more in details, we need to repeat some of the encryption basics. So in this presentation, it would be very simple. Encryption key, we will be using only encryption key, which is symmetric, meaning it is used to encrypt or decrypt the data, the same key. So we have a data, we have encryption algorithm, we have encryption key, and we can encrypt or decrypt it. That's it. Some of you might know the Alice and Bob, which just wanted to be speaking in private, and they are sending each other keys or something, and they don't want to be eavesdropped, but there's Eve, and she's getting the key, and she can decrypt and encrypt the data, which Bob can, without knowing that, without Bob knowing that she can do that. And there goes the problem. We cannot just like encrypt all of our data using one key, because in our case, if Eve gets the key, she gets access to the whole freaking infrastructure. She can decrypt anything. So we want to have some more granularity to it, and the first step is to have account key. Account key is an encryption key which is related to a single account. There we go. We have already a little bit of more granularity. We can do better than that, though. We have data keys, and the data keys encrypt the data. This process is called envelope encryption, for those who might want to know that, where you encrypt the encryption keys and store them securely. That is all done to just store everything securely, because the data in the database should be stored securely, the keys also should be stored securely, and we have account key which encrypts all of that. We have different databases, differently purposed, and we encrypt those the data in those databases with using different data keys. A little bit more granularity, a little bit more security layers. So just to recap, we have one account key, one entrance to the whole account encryption, and multiple data keys which it encrypts, and we're almost done, but how to manage the account key. And the account key is managed by the customer, which is one of the key differentiators of the write lock feature. Customer uses AWS KMS, Amazon Web Services Key Management System, to encrypt or decrypt the account key on demand. We send the just request, and AWS KMS provides us with a decrypted account key. So the customer is in charge of the data encryption in the account. Customer can retrieve the access to decrypt account key, rendering the data inaccessible not only to him, but also to us. That's what the write lock is about. So there might be some problems with AWS, because in all of the services we have, which are touching the sensitive data, we have this write lock implementation, which goes to database, gets the keys, talks to AWS, and it's in all of the services. They're reading the same databases, sending the request to decrypt probably the same account keys to AWS. This is a little bit not good, because routine time to decrypt account key using AWS KMS is 300 milliseconds, give or take. And we calculated that for months of work in our services in all of the data centers, we have around a day of waiting time just to decrypt the account keys. And the time is very valuable in a product like this, where you want to present the data to user as fast as possible. So we go to the second part of the presentation. We decided to do an encryption as a service. There's a little bit prehistory to that. We decided to go with the microservice platform. I'm not going to go too deep into it, because it's It's a very controversial topic. You might get something from it, might not get something from it, but we decided to go with it, and we faced the problem that some of the services which needed to be migrated to the microservices, they couldn't access the data because the Wrike lock implementation is in a monolith. We have a largely distributed monolith Wrike application that is, and we faced the problem of extracting the Wrike lock into the separate service. So when we have a service, we have a client. Let's talk about client. We want the client to be very lightweight. We want it to be included in all the services which need it. They will manage the user access, user permissions, whatever, and communicate with the AES and provide the encrypted and decrypted data on demand. How do we do this? Well, the first approach of sending data to encrypt or decrypt was kind of not very nice because the data can be quite large. The more data, the more problems on the network. And there is no caching because there are no meaningful IDs to the data. So we turned it down in order to have a different approach to communicate with the keys. We just send the request to have a key by ID, and it provides us with a key. The keys are very small, they're fixed in size, and they can be cached because they have IDs. So just to recap, this is legacy approach. All the services, they are communicating with AWS. And a new approach, we have the library, we have the keys going on, and there's a single point where we are accessing databases. We have access to AWS, which significantly improved our performance, and there is a lot of positive sides to this. So let's talk about the service itself. The benefits are, as I said, the fewer points of failure, easier to propagate the changes, new features or whatever. Also, you can monitor it better, and there is a decreased calls in AWS KMS. We calculated it is about roughly an hour now instead of a day in a month. Good. So we talked about caching a little bit, and we thought that caching might need to be in this presentation. So we have a caching by IDs. We cache in client the data keys, and we cache in ES the encryption management service account keys. In client, we cache data keys to decrease the amount of requests to ES. In ES, we cache account keys to decrease the amount of requests to AWS KMS. Everywhere to decrease the amount of requests, which kind of worked. But we cannot store the encryption keys indefinitely in cache. We need to have some kind of a timeout because it's a sensitive information. We also cannot, we have this promise to our customers that if they pull out the AWS KMS access, that it would render the data inaccessible to anyone, and we need to do this. Well, why not to do a cache invalidation synchronized like across the whole platform? We have a lot of services, and it would be quite a complicated solution, and it would be hell to monitor it. So we thought about some different solution, which is actually very neat, and it's asynchronous cache. It's a simple cache, except it has not one timeout, but two timeouts. One timeout for expiration and another for refresh. And before refresh should be lower than expiration. And before refresh, it behaves the same way as the regular cache does. But after refresh, it actually, the request to get some resource, in our case encryption key, it will be immediately satisfied, and there will be an asynchronous request to refresh the data. It's kind of hard to process it, so I will show it on a small example. So we have the consumer. That does work. Okay. We have a consumer. We request the resource from the cache, and there's a producer, right? So we request, cache requests the resource from the producer. Producer gives the key, and we have expiry and a refresh. Refresh as a half time. We decided to go with the half time for some reasons. So I will share it with you later if you want. But we have refresh less than expiry. The key is pushed back to consumer. Everyone is happy. 2 minutes later, we still have some expiry. We still have some refresh. Consumer requests the resource. Cache gives it back because it has it. Nothing happens. 1 minute later, we have still some expiry, but we don't have refresh. We already hit the refresh timeout. So the consumer requests the resource, and now the very interesting thing happens. The key is immediately propagated back to consumer, while the cache requests the resource. And in our case, it would be the request to resource would be a request to AWS or request to EES. Now producer gives the cache the key, consumer is satisfied, and the cache is updated with expiry of 5 minutes, refresh of 2.5 minutes, as it was in the beginning. The key thing here is that the consumer doesn't feel the latency when the key is refreshed. There are some downsides, of course, the 2 times increase in the call in both the services, but the upsides are also pretty sweet. The biggest load is only during the deploy. Well, we cannot get around that, but the network load afterwards would be pretty low. It would be gradual, like it would be homogeneous, but it would be low because it would be updating all the time in the background, not with the spikes of like 30 minutes or whatever. And for the clients, they will not see the, they will not feel on their request because they're in the pipeline of their request. There is no actually retrieval of the key from the service. What's the point of the service? Every little bit of improvement counts in software as a service, decrease in performance, being ready to expand the client base who are using the encryption as a service, because you can multiply these instances of the encryption as a service because it's stateless. And it also unlocks the microservice development with write clock enabled, because now the services can actually access the data in a microservice platform, not the monolith, distributed monolith-based approach. What to take out of it? I don't know. Transition to microservice is never easy in the big projects. Like you can have some downside, upsides. Every case is very unique. You need to really think on it. But it came with upsides for our infrastructure at least. And if you thought that you want to go with AWS KMS, but you thought that it might be actually too long to process the data there, well, with the cache and careful engineering, it might be proved useful, and you can give your clients a little bit more sense of control in your system. That's it. Thank you. I hope you liked it. Now to the questions. There will be this thing, which is by my colleague, also Riker, a very nice article.